Hi, everyone, and welcome, or hopefully welcome back to another episode of Reliability Matters. I'm your host, Mike Konrad. Today, we're diving into a topic that's reshaping how we think about thermal management, energy efficiency, and long-term performance in electronics manufacturing, low-temperature solder. Joining me today is Dr. HongWen Zhang, Principal Metallurgist and R&D Manager of the Alloy Group at Indium Corporation. Dr. Zhang is not only a seasoned material scientist with a Ph.D. in material science and engineering, a master's degree in material science and engineering and in mechanical engineering, and a bachelor's degree in metallurgical physical chemistry. He's also the co-inventor of Durafuse, a groundbreaking family of solder alloys that are redefining what's possible at low reflow temperatures, which reportedly does not compromise reliability. We'll dive into that claim soon. In this episode, we'll explore how low-temperature solders are helping manufacturers lower energy consumption, protect heat-sensitive components, and still meet the rigorous mechanical and environmental demands of today's electronics, from wearables to wafer-level packaging. We'll also talk about the challenges of brittleness, drop shock resistance, activation and encapsulation of no-clean activators, and how cutting-edge materials research is solving problems that used to be considered trade-offs. Whether you're a reliability engineer, a process expert, or just solder curious, this episode is packed with insights you won't want to miss. Let's get started.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
Dr. HongWen, thank you so much for being my guest today. I really appreciate you being here.
Yeah, thank you so much for having me.
Of course.
Nice meeting you here too.
Yes. I don't know if we've met in person before. I think I've heard you speak. You've spoken at PanPac before, right? In Hawaii.
Yes.
That's where
I think that
I met you there. I'm the chair of that conference, so I'm familiar with all of our speakers, and I'm like, I know he's spoken there before. Was it last year or earlier this year?
I think that's 2024.
Okay.
We meet in Hawaii. I think that's a great time for us to get together and learn from each other. That's a wonderful effort. Thank you so much for organizing that.
Okay, I'm going to do a little SMTA chair duty. I'm going to invite you back. So you can't go to Hawaii just once, right?
Exactly. That's a wonderful place. I think everyone should go there and enjoy the weather and enjoy the learning there.
Okay, sure. I'm going to say that's doctor's orders, right? So always follow what your doctor says. In this case, Dr. HongWen says go to PanPac, which is in early February of 26, and it'll be on the Big Island in Kona. So there we go. There's a little plug. Can you describe your role in the Alloy Group at Indium Corporation and how your team approaches the R&D of next-generation solder materials?
I think this is a good question for me. As I was promoted to R&D senior manager a few years ago, and I think that my major role in R&D Alloy Group is lead the development of the next generation of solder alloy to meet customer need or trying to catch up with the industry demand for the future. And also that I have to lead all my team working closely with our internal team and with customer to deliver the product which can be manufactured successfully in our end and in our customer side.
Well, that's quite a task. You have to have a scientific background and a little bit of a crystal ball to see into the future.
Yeah, exactly.
Because I'll guarantee you, yes, I'll guarantee you, by the time this episode is over, things have changed already, right? You're going to have to go back to the R&D drawing board and predict even more future.
That's correct. So we have to deliver on time. Otherwise, we will miss the opportunity. You are completely right.
Yeah, well, that's a lot of responsibility. The product you co-invented has been described as a mixed alloy system that enables both low temperature reflow and high reliability joints. Can you explain how that works? My understanding, at least in the early days of low temperature solder, is there were definitely some trade-offs there. Yes, low temperature, but there was always a but in there somewhere. Can you explain how that works and how it differs from traditional bismuth-based solders?
Sure. I think that all material developed and being used is not perfect. There's always some trade-off associated with the material being designed. I think that we developed this mixed solder system, and the final product we developed is called the Durafuse LT, is trying to deliver some alternative behavior which the traditional bismuth tin solder cannot deliver. Actually, this is majorly based on the mechanical shock brittleness of the traditional bismuth-based solder, because this is intrinsic to the bismuth phase exists in the solder material, and also some of other performance like the electrical migration issue is also associated with phase separation during the electron migration process, high current and a little bit higher temperature. And also another thing is actually lower melting temperature bismuth-based. Their melting temperature is always 138 degrees C. When people talking about the reliability to 125, actually based on the homologous temperature being calculated, bismuth-based alloy, bismuth tin actually, the homologous temperature is about 0.96. It's so close to the melting temperature. It definitely brings in some reliability concept. For the mixed solder system, Durafuse LT design, so we don't use bismuth in this design. So we use a bismuth-free indium containing alloy together with another tin, silver, copper powder in one paste system. The indium containing tin lead-free solder powder will provide a lower melting behavior, which allow a lower processing temperature, actual reflow temperature. And then during the reflow process, everything melt or merged together. So the reflow is actually a metallurgical process. To form, after reflow, we will form a uniform joint, which is still a tin, silver, copper, indium containing alloy, which has much better drop shock performance because we don't provide any of the, in the system, there's no any bismuth inside. So it's a bismuth free. So this is a provide performance on the drop shock strengthening mechanism. For bismuth-based alloy, this is a traditional low temperature solder. The intrinsic problem is from the bismuth phase, which is brittle. So mechanical drop shock performance and the electron migration is always a problem. And also that for the lower melting temperature bismuth tin-based alloy 138, if you are trying to serve at 125, sometimes aging or TCT environment, 125 temperature still too close to the melting temperature, make the homologous temperature 0.96, that's too high. That brings the risk for long-time reliability. For our design, we don't use bismuth containing alloy in the system. We are trying to use one alloy is an indium containing lead-free solder, so it's a tin indium, tin silver copper alloy, provide the lower melting temperature, allow us to processing at a lower temperature. And another alloy in the system we put in is a still tin silver copper. After reflow, the whole process will make a new alloy which has a different composition from alloy 1, alloy 2 in the initial paste. And the final melting temperature actually is higher than the low melting phase. So the melting temperature we design is close to tin lead solder, because people know tin lead solder is serving probably in the past very well for the whole industry, whose melting temperature 170 to 180 around, depends on how much silver you put in there. And our new alloy design system for the Durafuse RT is 180 degrees C, melting temperature to 200 degrees C melting temperature, so close to tin lead. So in the temperature wise, if you're trying to serve at 125, this alloy is definitely good enough to serve that. And also same time without any bismuth inside, so the mechanical drop shock performance and also electrical migration resistance is also higher, because we don't have those phase segregation, we don't have the brittle bismuth in this design.
I do miss the days of eutectic, of the old tin lead, because it was 1 degree it was solid, and then 1 degree higher it was liquid. You know, it was eutectic. It was instant. And those days are gone. Now we have all these plastic states, sludge states, as it starts to melt. In terms of the process window, in a traditional, say, SAC 305, there's a window of acceptable use. There's a low peak reflow temperature, a high peak reflow temperature, and that gives a little bit of room, a process room for the oven. Are low temperature solders proportionately, do they have a proportionately equal size window in terms of percentage, or is it a much tighter process window?
I think that for the design, for low processing temperature, we design for this alloy, you can use just really above the liquid temperature. The Durafuse RT we designed with a current version is 190 solid temperature, 205 liquid temperature. You can use for some BTC component, use barely just a 205 with a little bit longer plateau time, you can process right. But if you're trying to increase the temperature to 220 or just use a 605 profile, you can still process it without any problem.
Okay.
So this
So
alloy
if you buy a low temperature alloy and someone forgets it's low temperature and runs the wrong profile and runs a more traditional reflow temperature, everything still works. They just don't get the benefit of low temperature. Is that correct?
I think that's I didn't quite catch your question.
If someone confuses which alloy they're running through their oven and they run the wrong profile and they run a higher temperature, a more traditional temperature on a low temperature alloy, does that create reliability issues on its own, or is it quite happy to run at higher temperatures than it needs itself?
I think it really depends on how long your the melting temperature above liquid is.
Right.
Yeah, actually, if there's too long and you get a significant thicker IMC, probably that's a trouble for some of the component you have.
Right.
You probably have to reduce that, correct those kind of mistakes.
Yeah. You've shown in your presentations that your specific low temperature solder offers 2 orders of magnitude better drop shock resistance than conventional low temperature solders. What makes that performance leap possible? I mean, that's quite a, 2 orders of magnitude. That's a lot more drop shock resistance than a traditional low temperature solder. How do you account for that?
Yeah, actually, this is majorly depends on our alloy selection. So we select the bismuth free intrinsically, so we're trying to make the joint more ductile. And also because we select the indium in the system, in the traditional tin, silver, copper, we put indium in, lower the temperature. So indium actually, there are a few functions in the system. So number one, indium can form a solid solution with tin, if that's enough. Second thing, that indium, because indium tin, they are so close in the chemical reaction performance. So I think that in the periodic table, indium tin are neighboring each other. Indium is 49, tin is 50. So I think that on the interfacial IMC formation, indium participate as well. That will make the interfacial IMC more complicated, such as for the copper OSP surface finish. Instead of just forming the copper 16.5 IMC, indium will get involved. You may see copper 16 indium 5 IMC. That's complicated the IMC and slow down the IMC growth. So both on the ductility of the solder joint itself and the modification on the interfacial IMC formation, so you can get improved drop shock performance. That's a whole design idea for this system.
Are traditional low temp solders, do traditional low temp solders have less drop shock resistance than traditional temperature solders in general? Is that
Yes.
why there was an engineering effort to improve drop shock? Are they just known for yeah, you get the benefit of low temperature, but don't drop your circuit board on the ground.
Yeah.
So that was one of the challenges when you set out to do Durafuse, was to improve that particular attribute of the alloy, right?
Correct. I think that people know that tin silver copper are much better than bismuth tin based alloy in terms of drop shock. So what we are doing here is that we're trying to lower the temperature from tin silver copper and make it processable at a lower temperature, which is at least self-soldering with tin silver copper, but maintain the drop shock performance. That is a very, I think at the very beginning, our thought is we start from tin silver copper, but lower the temperature. That's the direction we go.
Yeah. Besides drop shock, what are the metallurgical challenges when creating alloys that reflow at lower temperatures but still maintain long-term mechanical integrity?
Actually, this is really depends on the reliability requirement you have. For bismuth tin alloy, because the melting temperature low, they're intrinsically, if you're trying to serve at a certain temperature like 125, that is a challenge. For our material, Durafuse LT design, so we abandon the bismuth. We directly use indium, which has very good on the ductility. And also after this mixed powder system design, after reflow, the melting temperature still around, current version is 190 to 205 range. So the melting temperature is much higher than 125 service temperature. So don't need to worry about the homologous temperature impact, which lower your service temperature, operation temperature. And also that the indium, as I mentioned, they involve into the strengthening. If you have more indium, your power indium will dissolve into tin matrix to form a solid solution. And also some of indium will react with the silver and the copper to complicate the IMC structure, make them not only just a silver 3 tin, but a silver 3 tin indium, not a copper 6 tin 5, but a copper 6 tin indium 5. Those kind of complication of the IMC structure precipitates will make them a little bit more stable, because the growth of them need more elements to diffuse to there to grow the IMC. So stabilize those kind of IMC structure precipitates will help on the reliability as well. So this is the whole design of our Durafuse system, Durafuse LT system. I have to mention that the Durafuse is not only one alloy system we designed. Based on the concept Durafuse, the mixed powder system, we do have high reliability solder being designed and put on the market. Also, we have high temperature lead-free solder paste system we designed and currently is under qualification for the power semiconductor industry.
So will the higher temperature versions of Durafuse technology also carry the attributes of increased drop shock and other mechanical attributes?
That's a different design system. I think that for the high temperature lead-free I mentioned, that's an alternative to the current highlight solder. This is because the regulation will highlight solder. So I think that currently still under exam, but no one knows when the exemption will be gone. So that's a different. For the high reliability, the melting temperature is same as the current 605 range, but provide much lower voiding performance and much higher reliability. So this is a different, because that for the high real solder is always currently people trying to design a very complicated system, put a more reinforced element into the system, but sometimes that will impact on the voiding performance. With a mixed solder system design, I think that we can make it processing and whiting well at the early stage of the reflow, but finally after whiting well, they can get more chance for the bubble to escape and achieve a low voiding performance. But finally, during reflow, everything still merges together. You can still get multiple reinforced elements to reinforce the final drop. So this is a design of Durafuse HR. We call it high reliability. So different, I think that material we design have different purpose. Durafuse RT, just one of them, facing on a lower temperature reflow, drop shock performance, and electron migration. resistance enhancement.
You talked about voiding. Are low temperature solders inherently better at reducing voiding, the same, or is voiding more of a concern? How does voiding fall? Because voiding has a lot to do with thermal profile and outgassing and the chemistry reaction and all those types of things. So how does the temperature affect, if it does, voiding?
I think temperature is only one of the factor impact on the voiding performance. I think that the right pace system design, right profile selection, and probably certain package dependent will have all have impact on the voiding. So we cannot just say, oh, low temperature solder is always good at voiding because the lower temperature. That's not the right statement.
I know that when it comes to reducing voiding, beyond the solder paste, there are a lot of mechanical tricks in the stencil design and even in the board design and even in masking designs and things like that that help clear the path for what would otherwise be entrapped air or chemistries. So there's I guess it takes a village of technological improvements to affect voiding. A kind of a sidebar question. When you sleep at night, do you dream about solder alloys? Does that just consume you?
I think that I work enough on the daytime. I don't want to work too much. I think that evening I can sleep very well without any dream.
All right. Just want to make sure that you don't spend all your waking and sleeping moments thinking about solder alloys. Let's talk about indium, not the corporation, but the element. How do indium-containing solders behave differently under thermal cycling, and what role does indium play in solder joint reliability as an element?
Yeah, I think that I mentioned a little bit before. So indium has a really close chemical reaction performance like a tin. And tin indium, they are dissolve each other in certain level. And only when you move to very high indium, you can get a low temperature indium tin eutectic. But close to a tin side, indium actually has a solid solution in pure tin. And because of a similar reaction, chemical reaction performance with traditional metallation or reinforcement element silver copper in tin silver copper, so they can complicate the precipitates. So the complicated precipitates, actually the growth coarsening behavior will be slowed down. They are more stable under the service temperature or the operation temperature. And also that depends on how much indium you put in there, the performance may be different. You cannot put too much. That will cause a low melting phase, actually will make a harmful impact. So well-designed system is needed.
Yeah, you don't want it too low. You don't want it to turn into gallium or mercury or anything like that. It needs to be solid in the jar, right?
Correct.
Low temperature
for the reliability. Sorry.
Yeah, no, go ahead. For reliability?
Yeah, for reliability and especially for the traditional reliability requirement 9404, 9704. I think that's a reliability requirement. So if it's 125, you definitely don't want to add too much. You still want the final joint melting temperature decent higher than the service or operation temperature.
Yeah. Low temperature solders seem to bridge the gap between high reliability requirements and thermal sensitivity in components. Are there any compromises that designers need to be aware of when adopting your specific alloy for low temperature solders in general?
I have to say that no solder module is perfect for everything. Yeah, so you must think that what is a drawback for each module. I think a lower temperature, as we mentioned. So if a bismuth tin based, the brittlness related with the bismuth and the electron migration related with the phase separation in the bismuth tin eutectic range, that's a concern for those material. For the indium container like the Durafuse RT design we do provide improve the drop shock performance and the reliability and the reflow temperature is in the lower range, but not as low as the bismuth tin-based alloy. So you still need the processing and under 205 peak temperature or a little bit higher, probably 220, which is similar to the tin lead solder module. Then you can achieve the optimized performance. So I think this is the difference of the design. I want to say that the Durafuse RT design actually is an alternative to the current bismuth tin-based alloy. So provide some benefit over bismuth tin. So this is what I want to say clearly to the industry. So select wisely with the demand you have.
Good advice. You've worked extensively with applications like wafer level packaging and BGA components. How does low temperature soldering benefit these packaging formats specifically?
I think that for the wafer level package, if it's for small wafer level package, like the single device of maybe 6 millimeter by 6 millimeter or slightly larger than that size, the design of low temperature solder itself probably may not impact that much, may not impact that. It's still the joint itself. I think that based on our experience, the joint, because that the wafer silicon is very rigid, the failure of wafer level package always, I think, that's close to the package side. It depends on how you select your paste relative to the ball alloy, make the joint to resist the stress concentration close to the chip side. That's a key to solve the issue, not the temperature itself. You can still use the SAC-05 to reach certain level, and also that you can select or compare with the ductile type or high reel solder or the rigid type high reel solder combined with stack ball to reinforce. From our experience so far, we learned is that the ductile type high reel solder paste combined with the SAC-05 ball provide some super performance than those rigid solder alloy with a SAC ball combination. So even that if you're trying to select some rigid ball alloy like a SAC Q, those kind of things, I think that we don't feel that will provide what you desire. That probably will worse, make the joint reliability worse. But it really depends on the package design as well. I think from what we tested, we do feel ductile will be better for wafer level package. But for BGA, I think that low temperature definitely will save energy. But for BGA reliability, if the BGA still surface with a SAC ball, you must be careful about the final joint morphology. If you get a hybrid joint, means that your SAC is reflowed, your package reflowed at a lower temperature. Your SAC-05 ball was not fully melt or not fully dissolved into a low melting temperature paste. You may have some concern on those hybrid joint because within the whole joint, the chip side, SAC-05 ball, and the bottom side, your low temperature solder, if their performance, mechanical response is totally different, you probably create some of the risk because you are not using the whole joint to accommodate the strength. Some of the weakness part of the whole joint, it depends on what solder alloy you use. Maybe the top side, the SAC side, or maybe the bottom side, the low temperature side. If any weakness side only to take over the stress concentration, you may still have risk. I think this is something you have to make some tests to prove the package you selected is good for the low temperature solder to pass the reliability. And I think recently for high performance computing, people talking about a very large size of BGA. That's probably 65 by 65 or even 120 by 120 size, those kind of a package. So warpage become a big concern.
Sure.
Under warpage impact, people may select lower temperature soldering because if lower temperature soldering can lower the warpage, the dynamic warpage, then that's some benefit. But still, people need to think about the SAC ball being used currently for most of the BGA because SAC ball never melt below 217. If you even still use a low temperature solder and to accommodate the warpage, your paste volume relative to both sides is still small. So you may still see the challenge. even you use a lower temperature. If the displacement at the latter reflow temperature you use is still higher than the paste itself can handle, you still get the risk. You see the non-wet open, head in pillow. You probably have to go with a little bit higher temperature to allow sac to dissolve more and then make that more paste flexible melting range, so they are flexible to accommodate any of the displacement. Or you can maybe ask your vendor to supply you the BGA with lower melting solder bowl attached BGA. That will help you to really run a low temperature solder benefit.
You talk about the energy savings. You mentioned that earlier. With so many companies now embracing sustainability programs, either voluntarily or because they're forced to by their customers, are there any that you're aware of documented studies that either by Indium Corporation or others that quantify what the energy savings would be if one were to compare a SAC 305, for example, with Durafuse or any other low temperature alloy that runs at lower temperatures? Is there a monetary ROI that's been established for that you're aware of?
Yes, I think that Indium, we do have some study already. I think that for the energy saving level, we do know that for the bismuth tin-based alloy, if you run under probably 170, 180 degrees C range compared to the traditional SAC 05 profile 240, you probably can save at least about 40% of the energy. And
Wow.
For Durafuse LT, we do know that if you are trying to reflow at a 205 to 10 degrees C range, your saving is probably about 20%.
Those are respectable numbers when you consider how much energy a multi-zone reflow oven requires. That's substantial. Are there specific either IPC or JEDEC or other standards that support or limit the adoption of low temperature soldering with mixed alloys like yours, or is standardization still catching up?
Yeah, I think that based on my understanding, I didn't see that the mixed solder paste being listed into IP standard yet. I think that's still catching up. So far, I think that to us, we have to work closely with our customer to qualify the material. Even the alloy design, actually the mixed solder paste design, still can go through the traditional reflow process. There's probably no difference or just a little bit of tweak on the current profile to adopt this mixed solder paste system. But we still need, I think, that working closely with customer and probably later with the IPC to make the catch up on the standard, to standardize this material.
I would imagine if not yet, soon there will be a number of Indium engineers sitting on the standards committees helping guide the new specification. Yeah.
That's true.
What applications would not be suitable for low temperature solders?
Can you explain a little bit, elaborate a little bit more on this?
Well, there are any specific applications, for example, where the electronics are deployed or assemblies with certain types of components that would not lend itself to whatever the few downsides are with low temperature solder, those would be amplified in those types of applications. Are there certain assemblers that are just not good candidates for low temperature solder?
Mm-hmm. Yeah, I think that based on my understanding, if the low temperature solder material provide enough performance, similar to the current SAC 05, I think everyone trying to use for the SMT process for sure.
Now, here's a long question for you. The question is going to read a little bit like a mini novel. While the principal critical factors with solder paste is the alloy, when we talk about solder paste, most people are concerned about the metal, right? Let's talk a little bit about the chemistry side of solder paste, namely the flux. Traditionally, the science behind no-clean flux relies on proper heat activation to volatilize the flux activators and other bad actors and or encapsulate those bad actors to render them inert. within the flux. The lower reflow temperatures associated with low temperature solders that are used in no clean applications specifically, where the board will not be cleaned, how is the flux sufficiently activated to volatilize or encapsulate the otherwise bad actors? And let me preface this with just a little anecdote. A few years ago, we and our friends at Foresight Laboratories conducted a DOE where we took a traditional SAC 305 and we determined the published minimum peak reflow temperature, and I think it was 218 or something like that. And we reflowed several boards at the lowest published peak reflow temperature. And then we started lowering the peak reflow temperature in roughly 1.5 degree increments. We ran a series of boards at 98% of the peak reflow temperature, and then 93%, and eventually 95%. So the highest variation was 5 degrees. 5%. 5%, which I can see an oven drifting 5%. That happens. And then we subjected all of the boards to SIR testing, surface insulation resistance testing. And we determined that the boards that were reflowed at the correct minimum peak reflow temperature all passed SIR testing under heat and humidity 168 hours, the IPC standard. The boards that were reflowed at 2% under passed, but barely passed. When we hit 5% under, all the boards failed. Every one of them failed, SIR. And that's because we didn't allow the heat within the reflow process to react with the chemistry side of the paste and do what it was supposed to do. We kind of changed the rules and did not allow the miracle of no clean to perform itself. And so when I hear of low temperature, I'm in the cleaning business, obviously, so that's why I'm asking this question. When I hear of low temperature solders, I can understand all the scientific research that went into the alloy side of it, the solder integrity, the bond, all the metallurgical stuff. Tell me about the chemistry side of it. Were there also changes made to the chemical formulations, to the flux, particularly in no clean, low temperature applications, so that the temperature in which all of the volatiles are properly encapsulated or activated can still be met at lower temperatures? Does that make sense?
I think the traditional Sector 5 alloy used flux may not be able to use for low temperature solder. I think that for the Durafuse RT system design, the flux design was different from what we commonly use for Sector 5. You have to pass SIR, which makes sure that your flux is fully activated and encapsulated right, without anything still active, which will impact on the SIR performance. That's the difference.
Yeah.
For low temperature, you need to redesign your system, your flux system.
Right. And is that on the radar? Is that something that your company or maybe if you're aware, other companies are looking to solve that side of the equation? I mean, you've solved the alloy side. 2 orders of magnitude better drop shock resistance, et cetera, et cetera. Is that something your customers are requesting, that in applications where they want to run no clean and not clean, and still have high degree of electrochemical migration prevention, ECM prevention? Is that a trade-off today, or is that something that you thought of already and mitigated that concern?
To us, I think for Durafuse RT design, this is our specific system. No one else have yet. So we already solved that problem.
Okay,
so the
good.
CF has no problem. I think customer already use this material for years, since 2020, already 5 years without any problem.
Okay,
I think this
good.
is okay. For bismuth tin-based alloy, I believe the major player of the world material supplier, they already have their solution. So I think so far for the ECM performance related with the low temperature solder, probably is not a red flag at all now.
Okay, good. Good. I was always wondering how that part worked, and I figured you guys thought of something. I just didn't know what that was. For reliability engineers listening today or watching the show today, what testing methods best demonstrate the performance of low temperature solder alloys? Is it maybe drop shock or thermal cycling or other types of analysis or something else?
Yeah, I do believe that, as I mentioned, no material is perfect.
Right.
For the low temperature solder to be used for reliability engineer, I think that the few things you must look at is what your reliability requirement. Is the drop shock critical or the TCT critical? And what is the TCT condition you are working at? Is 125 or 100 or 85 degrees C peak with a negative 40 or something like that? I think that this is always depends on the requirement. So the industry, I think that the whole industry provide a low temperature bismuth tin based alloy and alternative is a Durafuse RT system. They have a different probably performance aspect to solve something that probably is compensate each other. Because that the Durafuse RT still have their issue, which the melting temperature is still higher, so you cannot go with 185. If you really have a temperature sensitive component, you can only run 180 degrees C. You probably still need a true bismuth tin, but you have to think that how you can compensate on a drop shock performance. Or if you have high current issue, so you probably need to think about the EM electromigration problem as well. I think everything is data driven. Everything is data driven. But I think that from us and from all the industry, so each material we provide the boundary. So you can look at that and select, and still you need a test to make it a fit for your need.
Good advice. As I mentioned earlier, you presented at numerous conferences, and particularly the one in Hawaii, PanPac. What themes or technical debates or conversations are currently dominating the low temperature conversation in those technical circles? What are engineers talking about when it comes to low temp solder?
I think that from my understanding, the major things on the low temperature solder currently people debate is the bismuth tin based alloy. I think this alloy has been developed and tested 30 years ago when tin lead is moving away from the industry and moved towards the lead free, already being tested. And even now, recently, I think that 10 years ago, R&amp already start those low temperature solder project already 10 years. Is all focused on the bismuth tin based alloy. I think bismuth tin based alloy, people test it under certain conditions, people definitely can use. Probably focus on the 100, 110 peak temperature, probably service operation temperature, not be too high than that, because the melting of bismuth tin is still 138, which if it go 125, still some risk for lighter material. And the drop shock, another concern. And with together with electromigration, I think R&amp still have the project to present to the industry about electromigration performance on that part. That's some concern on that as well. Compared to traditional saxophone, it's still worse. I think this is a current debate. We are trying to provide the Durafuse RT, trying to make some improvement on the drop shock and the EM performance. I think that we can make this Durafuse RT system reflow at a lower temperature, but with the drop shock and the EM performance similar to saxophone. But the problem is the cost. Indium is not cheap at all. I think that everyone is looking at the performance, the processing window, and also the cost. In processing window-wise, I think that the Durafuse RT system still need 205 and above, even that we are working on even lower. We are working on probably 200 or 195 reflow material right now. But I think current version, you still need 205 and above to reflow the material well. So processing window costly, I think that's still not compete with bismuth tin yet. But
I think the challenge for Indium and any solder materials company is many times incorrectly, the solder paste is viewed as a commodity, and someone sells it for 2 cents a pound less, and the buyers just they're told to get a specific alloy, they get the alloy at the cheapest price. And when you mention that one of the downsides is cost, I can totally see that in the abstract. If one is just looking at cost, then of course that could be challenging. But if one then factors in reliability, escapes, defects, returns, RMAs, liability, then those costs are dwarfed compared to the downside. So it's really a big picture event. If I had my way,
Yes.
and I'm not in the soldering materials business. I have nothing to do with the soldering. We just clean up all the mess that you guys make, right? So that's what we do. We just clean the boards after they're done. But if I had my way, the engineers responsible for selecting the alloy and the flux chemistry side and all of that would dictate what the buyers have to buy. Then the buyers can negotiate the best price from whatever company. The problem is they'll say, yeah, we want a SAC 305, and then they'll just go around from company to company to company to company, and they may have the same alloy, but they may be different in terms of performance and chemistry side and things like that. So, if I had my way, the buyers would simply, their role would be to negotiate, not to shop around, to undercut the intent of the engineer who wrote out the statement of work and the whole production setup.
Yes,
without-
I think that. Yeah, sorry. Go ahead.
No, without giving away any trade secrets, you already mentioned one thing. You're working on even lower temperatures. What's next on the horizon for Indium Corporation Alloy Group, your group? Are you exploring new element systems, or you mentioned lower temperatures? So, is there anything exciting that you are free to tell me about?
Yeah, I think that for our side, for R&D, we are always looking for the cutting edge product based on customer need or industry need for the future. I think so far that I can tell is that we do working on the lower temperature, high reliability solder material, which probably is our goal that, okay, we can provide some material you can reflow, process at lower time, but the reliability even is comparable or comparable with the current all high real solder. So I think that people can buy this benefit with a lower temperature processing on energy saving and on processing window, wider processing window, but achieve reliability even much, much higher than the current high real solder people are using. I think that regarding to the previous question, I think that you are correct. Cost is only one piece of puzzle for people to select. I think for Indium, we are trying to provide some high-end material to solve the customer need on reliability, on some specific concern with the current routine user material. And we provide a very good service. I think that we work very close with our customer, whatever you need, and we will provide our suggestion, our solution for your urgent need. So that's a difference ourselves probably from some of our competitors. So provide not a cost saving material, but actually is a high reliability, high end material solution.
Yeah. Last question, because I know you need to go back and invent next year's technology. They're waiting for you. For companies hesitant to adopt low temperature soldering, what advice would you give? How would they start evaluating the reliability trade-offs and business benefits?
Yeah, I do believe that for an industry, if they really trying to adopt or don't want to adopt, that really depends on your own need. If your material or your package or your final product to the industry, so you're trying to use low temp based on the need, you can move forward with some data-driven solution. So you don't have to go lower if you don't have the need. But if you do see the benefit of that, no matter what is the benefit, higher reliability and some processing window, wider processing window to increase the yield or energy saving or some other benefit you have, you can try, but it's always data-driven. So don't just think that, low time is people are trying to try, I'm trying to try. No, that's not the case. Yeah. Think about your own need and starting to see the benefit, whether the benefit is enough to drive you move to lower temperature.
Look at the data. The data,
Yes.
Data is truth, assuming it's good data. Data is truth.
Correct.
Yeah.
Yes.
I agree.
Always counting on data.
That's great advice. Well, for my viewers and listeners that would like to get more information on these types of products, if you're watching this on YouTube, down here somewhere it says see more. You can click that, and I'll put some links to Indium Corporation's Durafuse products in there. And this is not a commercial for Indium Corporation or Durafuse. This happens to be what we're talking about today. And if you'd like to get more information on soldering materials in general, I'll put some links there as well. If you're listening to this on your favorite podcast app, go to your podcast app, look at the show notes, and that information will be there. Dr. HongWen, thank you so much for being my guest today. Thanks for educating me on this black art, this mysterious science of soldering materials and alloys and chemistries and things like that. I really appreciate your advice and everything you're doing for the industry at the end of the day to make electronic products more reliable. So keep up the good work. Try and get some sleep. Don't have nightmares about alloys and chemistries and things like that. And I'll look forward to seeing you at the next conference, hopefully in Hawaii.
Yeah, thank you so much for having me, and it's my pleasure to be here and to talk with you and share my thought on the low temperature soldering.
The pleasure's all mine. Thanks. And that's a wrap on another episode of Reliability Matters. Thanks for hanging out. Whether you listened on your favorite podcast app or watched on YouTube, I really appreciate you being here. If you haven't already, hit that subscribe button so you don't miss future episodes. On YouTube, give it a thumbs up and a subscribe. Those two very simple clicks really help us expand our reach. New shows drop every second and fourth Tuesday of the month, so mark your calendars. A huge thanks to PCB Chat from the Printed Circuit Engineering Association at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Got questions or an idea for a future episode? I'd love to hear from you. Shoot me an email at mike@reliabilitymatterspodcast.com. Want to learn more about the podcast? Head over to reliabilitymatterspodcast.com. Thanks so much for being here. Until next time, keep learning, keep doing it right, and remember, reliability matters. I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.